In 8b, moments of inertia, a uniform laminar rod, a uniform circular lamina of mass 8m and radius r can freely turn about a horizontal axis through P, perpendicular to the plane of the lamina. Now, perpendicular to the plane of the lamina means that if I was to draw a circle, okay, and basically, and this is my rotation point here, it means that it can rotate sort of like this way, something like that. So obviously not the scale, but it can rotate around like this, so it basically could end up here, you know. It has to be always attached to this point here, so it's rotating around, okay, like holding a CD by its edge and swirling it around, okay.
Sorry, sir, could you focus the screen a little bit?
Yeah. Okay, so particles of mass m are fixed at 4 points which are on the circumference of the lamina, which are the vertices of the square P, Q, or S. The compound body is set in motion. Okay, find the period of small oscillations of the compound pendulum, the length of the equivalent simple pendulum. Okay, so not an easy question to start off with. Okay, so what we're going to start off with, right? Here's an example of okay, so here's the full thing rewritten. Okay, it's rewritten with Q on top, P to the left, R to the right, and S. So it's like I rotated the full circle to the left. Okay, so we're going to figure out some distances. Okay, now the center of the circle, we have a distance, we have the radius. Okay, so you can see here the radius to each one. Now what we're going to do is we're going to figure out what the length, we can figure out what the length P to S is. Okay, to figure out what PS is, PS equals R squared. PS squared equals R squared plus R squared. Basically it's a right angled triangle where that's R, that's 90 degrees, and then you get PS squared equals 2R squared, and then PS equals root 2R. Okay, now next thing you gotta do when you're doing these compound questions is what's called moment of sum equals sum of moments. Okay, we're going to use that a lot. Moment of sum equals sum of moments. Okay, now where is it? It's horizontal axis through P, so P is the point at which it's rotating around. Okay, so what we're going to do next is moment of sum. Okay, now moment of sum is mh, okay, where h represents the distance to the compound pendulum. If I was to treat this all as one body, h would be the distance from P to its center of gravity. Okay, so all I have to do is have to figure out where that is. So what I can do next is I can say moment of sum, which is mh. Now capital M represents the full weight of the full pendulum, which is going to be 1, 2, 3, 4, 4 plus 8, 12m. Okay, so it's going to be 12mh. Okay, now I'm going to do the sum of moments. Okay, what we're going to do first is at Q. Now the trick is with the sum of the moments is it's the perpendicular distance from the fulcrum. So for example, if I go through Q right now with this green line here, how far is the green line away from P? R. So Q is going to be mgr. Okay, so the moment of Q is its weight by its distance away from the fulcrum. Okay, mgr. Now I'm going to have that's Q. Now I'm going to look at particle R. Particle R is how far away? This particle R here. Particle R is 2r away, so it's going to be mg2r. Okay? So it's going to be weight, it's going to be force times distance, mg times 2r. Okay? And then we're going to do g, which is in the middle. We'll call this g. Okay? How far it's that away? R. 8 mgr. Okay?
How come Q isn't root 2 or yeah?
Sorry?
How come Q isn't root 2 or
Q. Do you know the reason why? The reason why is this. It is a distance root 2r away, but it's what I drew earlier. It's not about how far Q is away, it's about its line of action of the force. So it's a perpendicular distance of r away. So that's something I got confused with first time around. Likewise G, its perpendicular distance is r away. For this one, its perpendicular distance, you can see it's 2r away from the green line. It's all about the line of the force as opposed to where the object is. Okay? So that's the difference. Okay, and now finally, what's the last one I have? Is it S? Yep, S. Now what do you think S is? Sorry? Mg or mgr. Okay, because this is now. What I forgot to put in for this one is it's actually the force. It's more. Sorry, I know I said m times h, but technically it's the force of the system, it's the weight of the system. Okay, but you'll see it actually turns out the same now in a second. So if I had 12 mg, what's going to happen to all the g's anyway? So the g's would go anyway. So technically you don't need the g's for this formula if it's force times distance for a moment. Okay, the m's are going to cancel as well. And what this will leave us is 12h equals 12 mg. Oh, sorry, 12. Sorry, just 12, isn't it? 12r. Sorry, excuse me, 12r. And then h equals r. Now that's what we expected, wasn't it? Because we expected that it's going to be the weight of the full system resides at the center of gravity g. Because why? It's symmetrical, isn't it? And for the most part, I think every time in the Lebenslauf course, it's always going to be symmetrical. Okay? So basically, you can see that this mg gets balanced by this one out here. This mg or q gets balanced by this one here. Hence why the center of gravity is still dead center. Okay? But I like to do the equation anyway, just to prove it. Okay? You might as well know the equation. Now that we've proved that it's all the weight is going through r, we're on the next part now, okay? We got to find out the inertia of the system. So I'm going to rub all this out and just leave h equals r, okay?
what does H stand for?
H is when I treat the full system as one. So this is the pivot point, and h represents the distance of the pivot point to the center of gravity of the full system, or not so much the center of gravity, but the line of force of the center of gravity. Okay? So obviously the line of force of the center of gravity is going down because it's weight, so it'll be vertically down. So it's basically another thing like it's rotational, like force times distance, moment of force. Okay? So now that we've established that h equals r, we're now going to go into the inertia of the system. We got to find the total inertia. Okay, so I'm going to call this I of r. Now, r is a point mass, isn't it? It's a mass that's on the system. Now, the formula for a point mass is md squared. Okay, so for r, it's going to be m times 2r squared. Okay. And that's going to get me 4 mr squared. For q, it's going to be, now this is where your root 2r comes in, because q is root 2r away from? It's root 2r away. Its inertia, its moment is distance r away, but regards inertia, it's still a distance root 2r away from the pivot point. So its actual distance only comes in when you're doing the inertia. Okay? So what's going to be, I of q is going to be m times root 2r squared, and that's going to get me 2mr squared. Okay? I of s, the point mass s is the same thing. It's going to be m times root 2r squared. It's going to get me 2mr squared. Okay. Now, time to get the equation of a lamina, circular lamina. I of a lamina, because remember this full thing represents a circle. Okay. So that's the circle it represents there. So it is a circle. Okay. So the circular lamina or a disc is a half mr squared, where r is the radius of the disc. Okay, so the radius of the disc is a half, m is 8m, and r squared, and we're going to get is 4mr squared. Okay, now the bad thing about the disc is the disc on its own, if it was rotating around this axis here, is great. So this is the moment of the disc. It was rotating about its center, and it was just going around in a circle, and it's staying in the same position. But that's not the case. The case is it's rotating around P. In order to fix this situation, we got to do what's called the parallel axis theorem. Okay, the parallel axis theorem states this: that the rotational energy of the lamina, so this is for the lamina, circular lamina, around P, it's going to be the the inertia of the lamina around P is the inertia of the lamina around its own axis plus md squared. Okay, where m is the mass of the lamina and d represents the distance of the center of gravity of the lamina away from the fulcrum or pivot point we're currently talking about. So we know that I lamina is mr squared, but what we need to know about md squared is it's here. That's the center of gravity of the lamina, and it's a distance r away. So we're going to have to add on another 8m r squared, bringing the grand total to 12m r squared. Okay. Now. Okay, so that was the parallel axis theorem. Okay, so what we're going to have to do now is find out the total inertia, or I total. I total is going to be I lamina plus IP plus IR plus IP plus IQ. Basically, I'm adding 4mr squared, 2mr squared, 2mr squared, and 12mr squared. When I add them all together, I'm going to get 20mr squared. So about P. So the total inertia around P is 20mr squared. Okay?
Why not add in the inertia of S?
Oh, sorry. I was meant to. Sorry. Oh, yes. Now, the only one I didn't add in the inertia of was P. Why does it have no inertia? Because it's located on the pivot point. It's located on the fulcrum. If you're located on the fulcrum, you have no inertia. Okay? Because it's rotating around P. Alright? Sorry?
It says IP, don't you?
Oh, sorry. This IP here?
No, instead of...
Ah, that's what I did. IP instead of IS. Sorry, excuse me. So here, this meant to be IS. Okay, so IR plus IS plus IQ plus I lambda. Yes, Dan?
Could you explain what the IP is above that though?
Like the 12 m squared.
Okay. Alright guys, just a quick reminder, IP, it means the laminate around P. It doesn't represent the particle P. Okay? So it's the laminate around P. So it's going to be a total of laminate plus IR plus IS plus IQ, and that gives us 20 mr squared. Now, we're asked for a simple pendulum. If you read back the start question, the period of small oscillation, of a compound pendulum. Now, the compound pendulum has a formula. T equals 2 pi root I over mgh. Okay? Now let me explain what everything means here. Oh, sorry, capital mgh. M is the mass of the full system, which is 12 m. G is G. I is the I is the inertia of the full system, which is 20 mr squared. H is what we talked about earlier. It represents the distance of the full system's center of gravity, the line of action of the force, away from the pivot point. We proved that to be R at the very beginning. Let's fill in the equation. 2 pi square root of I, which is 20 mr squared, divided by 12 m gr. Okay, m's cancel, r cancels with that r, and then we can 20 divided by 12 is the same as 5 over 3, so it's going to be 5r over 3g. Okay. Now, it next asks me to compare this to the period of a simple pendulum. Period of a simple pendulum is, you need to know the formula for a simple pendulum. It's 2 pi root L over G. It asks me for the equivalent simple pendulum. Equivalent means they're the same. It means they have the same period, which in turn means that it's going to be 2 pi square root of 5r over 3g. 2 pi's cancel, g's cancel. This means basically L equals 5r over 3. Okay guys, that's it.